Okay, we're going to go through an example question today, which is about energy transfers, calculating different types of energy, bit of efficiency. Let's dive straight in. Let's read the question. A 100-gram ball is dropped from 1.5 meters above the floor. Part A, how much gravitational potential energy is transferred as the ball falls to the floor? B, assuming no air resistance, how fast is the ball traveling right before it hits the floor? C, if the bounciness of the ball is 80% efficient and has a spring constant of 600,000, how much does the ball compress by? All right, let's start off with part A. How much gravitational potential energy is transferred? Well, we're going to start off by writing our equation for gravitational potential energy, and that is just the mass times the change in height times the gravitational field strength. I know that the mass of the ball, says in the question, is 100 grams. But first of all, I'm going to convert that. We don't want to use grams in physics, we want to use kilograms. So I'm going to divide that by 1,000, just in case you don't believe me. 100 divided by 1,000 is 1/10, or 0.1. So 0.1 kilograms. Kilo literally means 1,000, so 0.1 thousand grams. Okay, cool. So what about the change in height? Well, it says in the question that it's dropped from 1.5 meters above the floor. And meters is the right unit for this one, so that's fine. And gravitational field strength doesn't tell me, but luckily I remember that it's 9.8 meters per second squared, or you sometimes use newtons per kilogram. But there are my three numbers. All I need to do is put them into that equation. We've got the mass multiplied by the change in height multiplied by the gravitational field strength. So if I do that, that's going to give me 0.1 times 1.5 times 0.8, 1.47. And the unit will be joules because we're calculating an amount of energy. So that is part A. Okay, let's have a look at part B. It says, assuming no air resistance, how fast is the ball travelling right before it hits the floor? Well, I'm going to start off by writing down how much gravitational potential energy there was, which is 1.47 joules. Now, because there's no air resistance, I can assume that all of that is going into kinetic energy. So that means the kinetic energy also equals 1.47 joules, or rather I should say the gravitational potential energy that is transferred into this kinetic energy. So what's the equation for kinetic energy? It's half times mass times velocity squared, remembering from earlier that the mass we have is 0.1 kilograms. So now let's put the numbers into this equation. So I've got 1.47, the kinetic energy, equals half times the mass, which is 0.1, times, well, I don't know the velocity, that's the thing I'm trying to work out. Let's not forget that it's squared as well. So now I just want to rearrange this to find the velocity. So I'm going to divide both sides by this stuff here, and that will get velocity squared on its own at least. So dividing the left-hand side by that, 1.47 divided by half times 0.1, that equals velocity squared. And then I can get rid of the square by just taking the square root of both sides, and the square root of velocity squared is just velocity. So if I put all of this into my calculator, it should give me the right answer. So square root of big fraction 1.47 on top, and then underneath there's another fraction, half. My screen is being a bit strange here, but hopefully you can see. There we go, that's better. Times 0.1, and you can see that I've managed to type this in exactly as it appears on my page. That's what you always want to be going for. Double check your work as well. Really, really easy to make mistakes when you're typing it into a calculator. And then you can see here the answer I've got for velocity equals, I'm going to round it to 3 significant figures, which is pretty conventional. 5.42, and we've calculated a velocity, so the unit's going to be meters per second. There we go, part B done. Okay, so now let's have a look at part C. Now I'm actually going to take part C bit by bit. It starts off by saying if the bounciness of the ball is 80% efficient. Right, well, remember that we had the gravitational potential energy turning into the kinetic energy, and we assumed no air resistance, so that was 100% efficient. All of it went into that. And what this 80% efficient is saying, that only 80% of that kinetic energy is going to go into the elastic energy of squashing the ball. As the ball hits the floor, it's going to squash a little bit before it bounces back, and we're saying that it's going to get 80% of that total energy. So let's work out what that is. Well, the amount of gravitational and kinetic energy we had was 1.47. So 80% of that is just times by 0.8. If you want to turn a percentage into a decimal, you divide it by 100. So 1.47 multiplied by 0.8, 1.176. I'm just going to leave it like that for now. 1.176 joules. So that's how much elastic potential energy gets stored in the ball as it squashes. Now it says that this ball, let me just clarify, that is the elastic energy. And it says that this ball has a spring constant of 600,000. So let's write out our equation for elastic potential energy now. And that was half times K, which is the spring constant, times the extension, or how much it's been squashed, squared. And that's what we're looking for again. So we'll just put the numbers in. 1.176, the elastic energy, equals a half multiplied by 600,000 multiplied by the extension squared. We're going to rearrange this in exactly the same way that we rearranged the kinetic energy equation. We're going to divide both sides by this stuff here. So that gives me 1.176 divided by half times 600,000 equals, well, I could put the extension squared and then square root both sides. I'm just going to take a shortcut and say that I know I want to take the square root of both sides. So that's going to leave me with just the extension on that side and that on that side. So let's do that now. So I want the square root of a fraction, 1.176 on the top, and on the bottom I want half multiplied by 600,000. Apologies if you can't see my calculator screen very clearly. I'm just typing in exactly what I've got written here. That gives me the answer of 1.19789. So wherever I choose to round this is actually going to pretty much round to 0.002. So that is how much it squashes by. Now it's an extension, or it's a length, so that means we're measuring it in meters. And it might be more convenient to actually transfer this into millimeters. If I want to change something from meters into millimeters, milli means 1,000th. So I multiply that by 1,000, which is about 2 millimeters, which sounds about right. If I'm dropping a little bouncy ball on the floor, I'm going to expect it to squash by about 2 millimeters. So there you go. Quite a complicated example question. Lots of different parts, lots of different equations that I needed to use, but none of them too complicated. So make sure you brush up on those skills.